Still looking at compounding, but this time looking at a sequence of payments being compounded. We're going to define an annuity as a sequence of payments made at regular intervals. And the time period in which these payments are made is called the term of the annuity. An annuity in which payments are made at the end of each payment period is called an ordinary annuity. These are the types of annuities we're going to study. There's also one called an annuity due, in which payments are due at the beginning. An annuity in which payment periods coincide with the interest conversion period is called a simple annuity. There's also a complex annuity. To summarize, all the annuities we're going to look at are going to have terms that are given by fixed intervals. They're going to have payments that are equal in size and made on regular intervals. The payments are all going to be made at the end of the payment period. And finally, the payment period and the interest conversion period coincide. This is what it means to be an ordinary simple annuity. As I mentioned before, still thinking of this idea of compounding, but now we're making payments. So every payment we make is going to go through its own little compounding cycle. So we're going to consider a sum in example 1 of $100 paid into an account at the end of each month over a period of 12 months. And we're going to assume that this account earns 12% interest so that we can keep things very, very simple, and also compounded monthly. So it is an ordinary simple annuity. And so you can think back to our compounding formula for compound interest. So if we're thinking about our I, that 1 plus I to the n, then I is that R over M, and if our rate is 12%, well, that's 0.12, and we're compounded monthly. Well, there's 12 months in a year, so that's going to come up to 0.01. So you may recall us going through this when we were deriving that particular formula, but we're going to also consider that same scenario for each payment. So our first payment is going to get deposited at the end of the first month, and it's going to go in, and it's going to sit there, and it's going to get interest at the end of not the first month, but at the end of the second month, because it doesn't go in until the end of the first month. So this one is going to earn interest starting with the second month. So it's going to go from the second to the third to the fourth to the fifth to the sixth, all the way up to the 12th month. And if you count from 2 up to 12, that's going to be 11 compounding periods. So that's why we see this expression here. So that would be how much we've got from that one $100 payment. When we take our second payment of $100 and follow it through, well, it's not going to earn interest on the second month. It's going to start earning its interest at the end of the third month. So it's going to earn interest starting on the third month all the way up through the 12th month. And if you count 3 through 12, you're going to come up with 10 months. So we would get this expression for how much money is in from that $100 payment. So we could go through each payment and we could see the same type of scenario. And what you'll notice with the last payment, since it goes in at the very end of the very last month, it's not sitting in there for any amount of time, so it's not earning any interest. If we add up all of these values, I'm going to end up with $1268.25. So we're going to come up with a little formula down here that's going to give us that same answer. And this formula is based on a geometric series, which is out of the scope of this course, but you can look that up if you're curious as to how this formula is derived. So this is going to bring us to the future value of an annuity. So we call this S, and we think of that as a sum because that's what it's doing. It's summing up all of those payment accumulated values. So we take R, which is the payment amount, and we've got this little parenthesis of 1 plus I, and I is just like it was in the compounding formula. It's the R over M, raised to the N, which is the MT, just like it was in the compounding formula, minus 1, all over I, which is that same R over M. So let's write down what these variables are. S is the accumulated sum, which is also called the future value. So these problems are pretty easy to identify because they're going to say that you're depositing so much a month or so much a quarter or so much semi-annually, and you want to see what lump sum you're going to have at the end of whatever period you're saving for. So N is equal to number of payments. So remember that's that M times T. And remember M is the number of compounding times per year, and T is the number of years. Capital R is the amount of each payment. And I is that R over M, so it's that interest rate per period. Just like it's always been. So if we were to use our formula to get that value of the 1268.25, then we would have S is equal to, our payments were $100 a month, and our interest rate was 12% per year, and it was compounded monthly. So we would have 0.12 over 12, that's my R over M, raised to the MT power, so N is MT, compounded monthly, we just put it in for 1 year, and then this was over R over M. So if you wanted to go ahead and simplify that 0.12 over 12 to 0.01 like we had before, that would make your calculations easier in your calculator. And then you can type that in. Oops, so we had the 1268.25 before. And I'm going to go ahead and add the 1 plus the 0.01. And we do get the same thing, 1268 and 25. So that's the accumulated sum of all of those payments and the interest that each one made throughout the months for the first year. Like I mentioned before, this particular formula will be pretty easy to recognize when it needs to be used because it'll give you some sort of wording that says find the total amount that's going to be in the account or something to that effect. Here we have an example that a set of parents is saving for their child's college fund. They start at the end of the month of their child's first birthday. They decide to deposit $50 at the end of every month. They found an account that's paying interest at a rate of 5% per year, compounded monthly, and we're going to assume that that account is going to pay that same percentage for 17 more years. How much will the child have in their college fund by the time the child is 18 years old? We can see here how much will they have in their fund by the time. So we're looking for a future value here. We're looking for that accumulated sum. We do want this formula S, and of course this will be on the formula sheet, but your problems won't necessarily have the formula right next to them, so you'll have to be able to choose from the formula sheet which formula you're going to use. So let's underline some important information. This is going to be their payment each month, so let's go ahead and put that in there. And remember, I is equal to R over M. So the R is 5% per year. So we need to divide by M to get back to the compounding periods. Monthly would be 12. So we've got 1 plus 0.05 over 12. And remember, you can only simplify those decimals if they're exact like they were in the last example. And N is equal to MT. Here we've got monthly, so M is 12, and the time, it says for 17 more years, so times 17. So we've got 12 times 17 up here. Minus 1 over R over M. It's pretty difficult to get these parentheses right in your calculator, and as I always miss one somewhere the first time and have to end up typing something back in because my calculator gives me a nice little error message. But oftentimes it's easy to work backwards when you're thinking about parentheses. At least that's easier for me. I take my denominator, 0.5 over 12. I know that's going to have to be in parentheses in my calculator. And then I'm going to have that big division bar for my denominator. And then I'm going to have the whole numerator in parentheses as well. And then that 50 is just going to be out front for everything. But then I'm also going to have this 1 plus this stuff in parentheses. And I'm probably going to have that 12 times 17 in parentheses, unless I want to go ahead and multiply 12 times 17. And then don't forget that minus 1. That's really important. It'll give you an error message. Trust me, I've done it before. If you don't have that minus 1 in there. But then we probably also need some parentheses here with the 0.05 over 12. And I always miss this one. So if you get error messages, it's probably because you forgot. Right here, 1 plus this whole thing, if you'll notice, is raised to that power. So even though that fraction has parentheses, you need another one there because that whole thing is raised to the power. So notice what you can do. You can check your parentheses by looking here, and then by looking here. So just lining everything up to make sure you've got everything in place. And I think we should be good. And the only other extra one you might want to put, you could put one extra one here and here to show that 50 is multiplied by everything. But 50 times the numerator should work out. So those would just be extra. All right, so get this typed in. Never hurts to practice. So if you want to leave that third one out, we'll just see what happens when we don't. So let's leave that one out and see what happens. Shouldn't really need it. All right, so 50 double parenthesis, 1 plus, and keep going. Okay, so it looks like we get an accumulated value of future value. So this is the FV of 16,026, and we're rounding to cents since this is money, and so we get 23 cents. So when that child turned 18 years old, they will have the $16,026 just because their parents set aside $50 at the end of every month. So you'll notice I have something over on the side called Using TI's TVM Solver app. So that's great news for those of you who don't like these formulas. Now I am going to encourage you, however, to try both because oftentimes on a test, if you get a little mixed up over here, you're not sure what to do, your formula is going to be your fallback. So it's always a good idea to think about both things, okay? So N is going to be your number of payments, and first of all, I guess I should tell you how to get there. We're going to go to APPS, which is this little button right here next to Math, so down 3 over 1, and hit Enter on Finance, and hit Enter on TVM Solver. And this can't be deleted, so it has to be on your calculator somewhere. So N is equal to number of payments, so that's the MT right there. So I've got 12 times 17. You don't even have to do that ahead of time. Hit Enter. The percent, this is the key. Notice I've put an interest rate as a percent, not a decimal, so that's something you'll have to remember. Just as 5. Present value, it's not starting with anything in the account. If it did start with something in the account, though, that would have to be a negative number. Anything that's paid into an account from you has to be a negative number. We're making payments here, or the parents are, $50, and it's paid in, so that's going to be negative. And we're trying to figure out the future value, so for right now we're just going to put a 0 there. So let's start filling this stuff in. So 204.5, nothing in the account to start with. If there was, we would have a negative with whatever number, payment, $50, and then future value is what we're trying to figure out. Let's just put a question mark on our paper and then this is compounded monthly. These two numbers will always be the same. So you don't see alpha enter at the bottom, but that is what you do when you put your cursor up here on the future value mark. So put it on the 0, and the alpha is the one underneath the second button, mine's green, and then hit enter, and it automatically gives you that magical number. So 16, 26, and 23. Okay. The key is having that negative in the right place. Because notice, if I go up and I take that negative away off that payment, and I do alpha enter right here, it's going to tell me that my future value is a negative amount of money. And that doesn't make sense. So we need to make sure that whatever we're paying in is a negative value, so that when we compute the future value that's in the account, then that's going to be a positive number.